Hello student, I am Nirmala Morade, Department of Mathematics from S.V.K.T College, Devali Camp, Nasik. In today's lecture, we will study what is the relation between line and plane, that is find the point of intersection of line and plane and find the equation of plane if that line lies on the plane. This topic is included in the unit line of FYBSc from paper geometry. So, suppose I consider a line and the plane, then what are the possibilities between them? Whether line intersects the plane or it does not intersect the plane or it lies on the plane. Now see all these three diagrams. In first diagram, this is a line and plane. Line does not intersect plane or line does not lie on the plane also. In second case, in this case we can say that they are parallel to each other. In second case, see here, the line intersect the plane at a single point. They are intersect each other at a single point. And in third case, the line totally lies on the plane. So in today's lecture, we will see the situation first and the second, how to find the point of intersection of a line and plane, and next how to find, show that the line totally lies on the plane and find the equation of plane containing this given line. So let us consider the first problem. So now let us try to clear all this concept by using one example. Find the point of intersection of the line x plus 1 upon 1 is equals to y plus 3 upon 3 is equal to z minus 2 upon minus 2 and the plane 3x plus 4y plus 5z equals to 5. So to solve this problem, or suppose I want to check whether the line intersects the plane or not. So for that we find the arbitrary point of the line and then put that arbitrary point or coordinate of the arbitrary point in the equation of the plane. So we get one equation in terms of that constant. So let us first find the arbitrary point of the line. So this is the given line. Since we want to find an arbitrary general point of the line, suppose this is equals to some constant, say we take equals to r. Then equate each ratio equals to r, that is we consider x plus 1 upon 1 is equals to r. Solve this equation for x. So this can be written as x plus 1 is equals to cross multiplication is equals to r. So it gives x is equals to 1 r minus 1. Equate first ratio is equals to r. So we get this equation. Solve this equation for r x. So we get x equals to r minus 1. Do the same procedure for the second ratio. So equate y plus 3 upon 3 is equals to r. So solve this for y. So y plus 3, take the cross multiplication, equals to 3r, which is same as y is equals to 3r minus 3. This is the value of y. Similarly do the last one. Z minus 2 upon minus 2 is equals to r. Now solve this for z. So we will get here z equals to minus 2r plus 2. So these are the coordinates of arbitrary or the general point on the line. Since for different value of r we will get the different points on the line. This is our first step to find the arbitrary point of the line. So since here we want to find the point of intersection of line and plane. So in case of intersection of line and plane, there is a one point of intersection. So suppose this is a point of intersection, we denote by M. Line intersect the plane or plane intersect the line at point M. They meet each other at point M. So the point M lies on the line as well as the plane. So since it lies on the line, so for some value of r, this will give the coordinate of M. So for some r, these three numbers gives the coordinate of M. So M has coordinate x is equals to r minus 1, y is equals to 3r minus 3 and z is equals to minus 2r plus 2. Okay, this point, the point M also lies on the plane. The point M also lies on the plane. So these coordinates satisfy the equation of the plane. So we substitute here x equals to r minus 1, y is equals to 3r minus 3 and z equals to minus 2r plus 2 in the equation of plane. So given equation is three x plus 4y plus 5z is equals to 5. Now substitute all these three values here. So 3 as it is. Now put the value of x, which is r minus 1. Then put the value of y, which is 3r minus 3. Now then put the value of z, which is minus 2r plus 2. Okay, now this is one equation in R. We have to solve this equation for R. So just simplify this. Open the bracket. 3r minus 3 plus 4 into 3r is 12r minus 4 into 3 is 12. Next one is 5 into minus 2r is minus 10r plus 10 is equals to 5. So now collect the terms of r here. This is 3r plus 12r is 15r. 15r minus 10r is 5r. So into minus 5r. Now collect the terms of constant term. So here minus 3 minus 12 is minus 15. Minus 15 plus 10 is minus 5 is equals to 5. Again see there, minus 3 minus 15 plus 10 is minus 5 is equals to 5. So this is same as 5r equals to, shift this to another side, so it becomes 10, and so divide by 5 we will get here r is equals to 2. So since we get the unique value of r, see here, since we get the unique value of r, we can say that the line intersect the plane at a unique point. That is, line intersect the plane, and this value should be a real value. This is the real value. Now r equals to 2. Now put this value in the general equation or in value of coordinates of M. So here, since we get the unique value r is equals to 1, so we say that line intersects plane, given plane, and to find the point of intersection we should put r equals to 2 in the coordinates of M. So we know that M has coordinate x is equals to r minus 1, y is equals to 3r minus 3, and z is equals to minus 2r plus 2. These are the coordinates of M. So now substitute here r is equals to 2. So we get the required point of intersection. So now here x coordinate of the point of intersection is 2 minus 1 is 1, y is equals to 3 into 2 minus 3, z equals to minus 2 minus plus 2 equals plus 2. So just solve here. This is 6 minus 2 is 3. This is minus 4 plus 2 is plus 2. So these are the coordinates of point of intersection. So in general, remember the steps. Suppose we want to find or check whether line intersect the plane or not. So first step is find the arbitrary point of the line. So for some value of that r, we will get the point of intersection. Put that values of x, y, z, that is coordinates of the point of intersection, in the equation of plane. Solve that equation for r. So we will get the unique value of r, which is real. Then we say that line intersect the plane. And putting that value of r in the coordinate, that is in the coordinate of M, we will get the point of intersection. Okay, our second condition is when we say that that line lies on the plane. So for that we should find a condition for that the line lies on the plane. So our question is here, find the condition a line to lie on a plane. So we consider a plane and we want to find a condition for that the line lie on the plane. So now for that first we consider the equation of line. So suppose we denote this is a line L, we consider its symmetrical form. X minus x1 upon a1 equals to y minus y1 upon b1 equals to z minus z1 upon c1. Here line is passing through the point x1, y1, z1 and having DRS a1, b1, c1. These are the DRS of the line. And we consider the equation of plane as, we denote this plane by pi, x ax or a to x plus b to y plus c to z plus d or d2 is equals to 0. This is the equation of plane. Now here we know that a2, b2, c2 denotes the DRS of the normal to the plane. So we want to find a condition, a line to lie on a plane. So first of all, the line L is passing through the point x1, y1, z1. So this is a point on the line, and second its DRS are a1, b1, c1. And second, suppose this is a normal to the plane. We draw a normal. Normal means a line which is perpendicular to the plane, having DRS a2, b2, c2. So suppose we assume that the line lies on the plane. Line lies on the plane. So now first we have to find the arbitrary point of the line. Find the arbitrary point of the line. So x minus x1 upon a1 equals to y minus b1, y minus y1 upon b1 equals to z minus z1 upon c1. To find the arbitrary point, we equate each ratio equals to say r. So solve this equate each ratio equals to R and solve for x, y, z. So we put x minus x1 upon a1 is equals to R. So we will get here x is equals to a1r plus x1 or x1 plus a1r. Similarly, equate the second ratio equals to R. We will get the value of y, which is y1 plus b1r. And last, z, equating the last ratio equals to R, we will get z1 plus c1r. So this is the general. This is a general or the arbitrary point of the on the line. So now we assume that line lies on the plane. So this arbitrary point also satisfies the equation of the plane. So now we put this in the equation of the plane. a2x plus b2y plus c2z plus d2 is equals to 0. So this a2 is as it is, replace x by x1 plus a1r plus keep this b2 as it is, put y equals to y1 plus b1r plus c2 as it is, put the value of z, which is z1 plus c1r plus d2 is equals to 0. Now here we have to open the bracket first. So this becomes a2x1 plus a2a1r plus b2y1 plus b2b1r plus c2z1 plus c2c1r plus d2 equals to 0. We just solve the equation. Now next step is we have to collect the terms of R and constant term together. So I write first the terms without R together. So we have to underline all these terms by a single underline. Now I write all these terms in a one bracket. So that are x2 x1, b2 y1, c2 z1 plus d2. Again see, I write all these terms a2x, b2y, c2z1 and d2 in one bracket plus the remaining term contains R, take R as a common and write other terms in a bracket. So from remaining terms we take R common. So remaining terms are a1 a2, next term is b1 b2, next term is c1 c2. So when we say that the line lies on the plane, if each and every point of the line lies on the plane, that is this equation is true for every value of R, and it is true for every value of R if and only both the brackets should be 0. Again here, when we say that the given line lies on the plane, if each and every point of the line lies on the plane, that is this final equation is true for every R, and when it is true if both brackets are 0 here. This is true for every R if both the brackets are 0, that is the first condition a2x1 plus b2y1 plus c2z1 plus d2 is equals to 0, and the second condition is, or the second bracket should be 0. So these are the two conditions for that the given line lies on the plane. Observe the first condition, which is a2x1 plus b2y1 plus c2z1 plus d2 equals to 0. So this condition says that the point x1, y1, z1, which is the point of the line, lies on the plane. So at least one point of the line should lie on the plane. So what is the meaning of this first condition? One point of line lies on plane. And the condition second say a1 a2 plus b1 b2 plus c1 c2 is equals to 0. It indicates that the line is perpendicular to the plane. Line is, or you can write a1 a2 normal is perpendicular to the line. So now see what is the condition a1 a2 plus b1 b2. This is a condition of two perpendicular lines. Among these a1 b1 c1 are the DRS of normal to the line, DRS of first line, and a2 b2 c2 are DRS of normal line. So this sum is 0 indicates line is perpendicular to the normal line, that is plane is parallel to the line. So these are the two conditions for when a line lie on the plane. Now let us consider the problem related to this theory. So remember here again, when we say that the given line lies on the plane, here x minus x1 upon a1 equals to y minus y1 upon b1 equals to z minus z1 upon c1, and the equation of plane is a2x plus b2y plus c2z plus d2 equals to 0. The first condition is x1, y1, z1 is a point on the line that should lie on the plane, and second condition is these numbers a1, a2 plus b1, b2 plus c1, c2 equals to 0. That is normal is perpendicular to the line or plane is parallel to the line. So remember these two conditions. So let us consider a problem. See, this is our problem. Show that the line x plus 10 upon 1 is equals to 8 minus y upon 2 is equals to z lies on the plane. Actually, there are two methods. The first one is apply our theory method, or otherwise check these two conditions. Both methods are same. So now here I apply the theory method. So first we have to find the arbitrary point of the line and put in the equation of the plane. So now here, to find the arbitrary point, we consider x plus 10 upon 1, 8 minus 1 upon 2 is equals to z, say is equals to r. Now from this, equate each ratio equals to r and find the value of x, y, z. I write directly here. So here x equals to r minus 10, y is equals to 2r. So here first 8 minus y equals to 2r. So here 8 minus 2r is equals to y, and last z equals to r. So equate first ratio equals to r, solve for x, then equate second ratio equals to r, solve for y, and similarly for z. So the arbitrary point is x equals to r minus 10, y is equals to 8 minus 2r, and z equals to r. This is the arbitrary or general point of the line. Now substitute these coordinates in the equation of plane. So given plane is x plus 2y plus 3z is equals to 6. Now we substitute these values. So this equation becomes r minus 10 plus 2 times 8 minus 2r plus 3 into r equals to 6. So this is say that r minus 10. Now just simplify it, open all the brackets. So 16 minus 4r plus 3r equals to 6. Therefore, see here, if we select the terms of r here, r minus 4r is minus 3r, that gets cancelled with this 3r. So all these terms gets cancelled, there is no term of r. Then collect the constant terms here. So minus 10 plus 6 is 6 equals to 6. This equation is always true here. That is every point, arbitrary point satisfies the equation of the plane. So each and every point of the line lies on the plane, and so line lies on the plane. So this is one method to check whether the given line lies on the plane, or otherwise this is the another method. Now let us solve this problem by using the second method, by using these two conditions. Okay. So this is the first method. In first method, directly we have to find the arbitrary point. Now put that arbitrary point in the equation of the plane. So we get an equation which is always true, then line lies on the plane, otherwise not. And the second method is this one, using these two conditions. So our second method is, according to the second method, one point of the line should lie on the plane, and second, this condition is true. So now for that, write a point of the line. So I consider the x plus 10 upon 1 equals to, I rewrite the second term here, which can be written as minus y minus 8 upon 2. I take first minus sign common and again I adjust with this one, and equals to z minus 0 upon 1. So compare this equation with x minus a1 upon x minus x1 upon a1, y minus y1 upon b1, and z minus z1 upon c1. So these three numbers are always the DRS of the line. So DRS of the line, a1 is 1, b1 is minus 2, and c1 is equals to 1. And these three numbers, if I compare these numbers, that is, write the value of x1, y1, z1. So here x1 equals to minus x1 equals to 10. Just here, if I compare these two terms, x plus 10 is equals to x minus x1, x gets cancelled, 10 equals to minus x1, that is x1 is minus 10. Okay. Next, minus y1, here minus 8. So directly comparison gives y1 equals to 8. And here also z minus 0, z minus z1. So we get z1 equals to 0. So remember, minus 10, 8 and 0, this is one point on the line, and 1 minus 2 minus 1, these three numbers are DRS of the line. Okay. Now next, consider the equation of the plane. So equation of the plane is x plus 2y plus 3z is equals to 6. Now compare this equation with a2x plus b2y plus c2z plus d2 is equals to 0. You can rewrite this also by shifting minus 6 to plus 6 to another side. So it becomes minus 6 equals to 0. I just shift this term to the left hand side. So it becomes minus 6. Now compare and find the value of a2, b2, c2. So now here a2 is 1, b2 is 2, c2 is 3, and d2 is minus 6. Okay. Now our first condition is the point x1, y1, z1 should satisfy the equation of the plane. So write this first condition. Either remember this one and check whether this is 0 or not. So a2 is 1, and x1 is minus 10, b2 is 2, y1 is 8. I just put all these numbers. a2 is 1, b2 2, c2 is 3, and z1 is 0 here, plus d2 is minus 6. Check whether it is 0 or if I put in this equation, so it becomes minus 10 plus 16 minus 6 equals to 0. So we get 0 equals to 0, that is right hand side equals to left hand side. So first condition is true. What is our second condition? a1 a2 plus b1 b2 plus c1 c2 should be 0. So we check whether it is 0 or not. So put the values of these constants. So a1 is 1 and a2 is also 1. Then b1 is minus 2. From here it is minus 2 and b2 is also 2 here. c1 is 1 and c2 is 3. 1 and 3. So solve this one. 1 minus 4 plus 3. So you can solve here and you can check here 0 is equals to 0. So both conditions are true here. So given line lies on the plane. Okay. So now our second part is, suppose the line lies on the plane. Suppose we have to given the equation of plane and we have to find the equation of, we have to given the equation of the line and we have to find the equation of plane which passing through the given point and containing the given line. So for that, see the next question. So question is, find the equation of plane which passes through one point and the line or containing the line x minus x2 upon a equals to y minus y2 upon b equals to z minus z2 upon c. So suppose this is a plane and the plane is passing through this point. So I write here, so point is x1, y1, z1, and also the plane contains the line. So this is the equation of line. From this we can say that here this line is passing through the point x2, y2, z2. The line is also passing through the point x2, y2 and z2, and DRS of the line are ABC, small ABC. And we want to find the equation of the plane. So now we know the equation of plane which passing through one single point. This plane is also passing through the point x1, y1, z1. So equation of the plane which is passing through the point x1, y1, z1 and having DRS capital A, B, C of its normal. So the equation of required plane is A into x minus x1 plus b into y minus y1 plus c into z minus z1 equals to 0. The required plane is passing through the point x1, y1, z1. So its equation is in the form capital A into x minus x1 plus b into y minus y1 plus c into z minus z1 equals to 0. Okay, next one is the plane also passing through this point x2, y2, z2, because this line lies on the plane. So plane is also passing through this point, and so equation of plane satisfy, the coordinates of this point satisfy the equation of the plane, that is 1. So in equation 1 we put x equals to x2, y is equals to y2 and z equals to z2. So we get here a times x2 minus x1 plus b times y2 minus y1 plus c times z2 minus z1 equals to 0. I denote this as equation 2nd. So this is the second condition. Now next one is the DRS of normal. So suppose I draw, this is a normal to the plane and its DRS we have to denote it by capital ABC, and small ABC are the DRS of a line which is completely lies on the plane. So what is the relation between this line and the plane? Obviously they are perpendicular to each other, and since these two lines are perpendicular to each other, by using the condition of perpendicular lines we will get this condition: A into A plus B into B plus C into C is equals to 0. This is the third one is. So now we illuminate capital ABC from these three equations, equation 1, 2 and 3. We will get these three equations, all these three equations for ABC, so we will get the required answer. So now for that we have illuminating capital ABC from these three equations, we have the determinant write the coefficient of capital A, B and C. We have to eliminate capital ABC from this equation. So write a determinant whose first row is related to the equation 1 by taking the coefficients of capital ABC. So that are x minus x1, y minus y1, z minus z1. Now from equation 2nd, do the same thing, write the coefficient of ABC as a second row elements. So we get here x2 minus x1, y2 minus y1, z2 minus z1. And last from equation 3rd, coefficients of capital ABC are A, B and C. And since we have to eliminate these three constants ABC from these three equations, we have this determinant equals to 0. Now solving this determinant, we will get the required equation of a plane, that is equation of plane which passing through the point x1, y1, z1 and containing the line x minus x2 upon A equals to y minus y2 upon B equals to z minus z2 upon C. So remember, this is the equation of a plane, required equation of the plane. So here notations are x1, y1, z1 denotes or is a point on the given line. Next, is a point on the given point, and x2, y2, z2 is a point on the line, and small ABC are the DRS of the normal to the line. So at the end of the session, now let us consider a simple problem using this result. Find the equation of plane containing the line x plus 1 upon minus 3, y minus 3 upon 2, z plus 2 upon 1 and the point 0, 7, minus 7. See what is the question. Find the equation of plane containing the line and the plane. So now for that we use this. This is the equation of the plane. This is the equation of the plane containing one line and the point. So now here the point is x1, y1, z1, which is we have to given 0, 7, minus 7. This is a point on the plane. Second, from this equation, we write the equation of the line x plus 1 upon minus 3, y minus 3 upon 2, z plus 2 upon 1. This is the equation of line. Either remember what is the point on this line and the DRS of the line, or otherwise compare this equation with this one. X minus x2 upon a, y minus y2 upon b, and z minus z1 upon z2 upon c. So if we compare these two equations, we will get here a is equals to minus 3, b is 2, and c is equals to 1. And next one is find the point on the line x2 equals to, here plus 1 and here minus x2. So here take minus 1. Y minus 3, y minus y2. So y2 is 3 here. And similarly z2 is minus 2. Again see how to write the point on the line. X plus 1 is same as x minus x2. So x2 is minus 1. Y minus 3 is equals to y minus y2. So y is 3. And similarly here z2 is minus 2. Now we have to find the equation of the plane which contains the given point, containing given point and given line. So its required equation is this one. Determinant of this determinant equals to 0. Now we have to put all the values and just solve the determinant. So we will get the required answer. Therefore, so x minus, put all these values, x minus 0, y minus 7 and z plus 7. I have to put here x1, y1, z1. Next, x2 minus x1 you can put directly or you can take subtraction also. This is x2, this is x1. So which is same as minus 1 minus 0, 3 minus 7, minus 2 plus 7. I have to put x2, y2, z2, x1, y1, z1. And now put the values of ABC. Those are minus 2, 2 and 1. And this determinant equals to 0. Okay, I first rewrite, just simplify the second row. So first row is x, y minus 7, z plus 7. Next row is minus 1, minus 4, which is next 5, minus 3. Just rewrite the second row here. Is equals to 0. Now solve the determinant. So this is same as x times, do the product of these two, which is minus 4, minus product of these two, which is minus 10, minus, take this number as it is, minus x minus 4, then delete the middle elements. So product of these two, product of these two is minus 1 and product of these two is minus 15, minus plus 15. I just solved the 3 by 3 determinant. You can easily do this, and simplifying we will get the answer. The last term is here z plus 7 times, write the last term, which is same as minus 2 and minus 12, put equals to 0. So simplify this equation. So first term is minus 14x, next term is plus 14 y minus 7, next term is minus 14 z plus 7 is equals to 0. I just solve this one. So this becomes minus 14x plus 14y minus 14 into 7 minus 14z minus 14 into 7 equals to 0. So this is same as, we divide throughout by 14 also, na? So 14 gets cancelled. First divide throughout by 14, that is easy for us. So 14 gets cancelled. Rewrite the equation, x plus y minus 7 minus 7 equals to 0. So this is same as minus x plus y minus 7, sorry, minus z minus 14. I just simplified and now rewrite it again, multiplying it by minus 1. So it will take the our regular or general form. X minus y plus z plus 14 equals to 0. So this is a required equation of plane containing given point and the given line. So in today's lecture, we will see how to find the relation, whether line intersect the plane, how to find the point of intersection of line and plane. If also what are the conditions so that line lies on the plane and equation of plane containing the given line. These are the three important points in today's lecture. First, how to find the point of intersection of line and plane, how to show that line lies on the plane and equation of the plane containing the given point and the given line. In next lecture, we will see what are the condition of the coplanar lines. So, thank you. Today we stop here.